Thank you guys for all showing up. We have a really cool event today with Professor Kleinrock of the Computer Science Department. He's a legend both within the department and also outside of the department. He's been here for more years than I've been alive, and I'm sure that there's been many stories that I've come with. Before he was at UCLA, he was also a student at MIT, and with that, interacted with Claude Shannon many times. And so the focus of the event today will be the Bit Player, which is actually a documentary on the life and work of Claude Shannon. So I won't bore you too much with the details, and I'll let Professor Kleinrock speak, because I know that's what we're all here for. So yeah, take it away.
Thank you, Jason. I'll get my rig here. So welcome. You're going to have a great event today. How many of you have heard of Claude Shannon prior to tonight? A little more than half. Shame on the rest of you. You'll learn about him today, and then read about him. He's done some great work. For example, I'll talk about this in a moment, but this was his classic work, and it's called A Mathematical Theory of Communication. Rohit, would you pull up the book, your copy you have of it, and please read the title of that book? It's called The Mathematical Theory of Communication. Shannon published it with A Mathematical Theory. Then this guy named Weaver wrote a book with Shannon about this, and he changed it to The Mathematical. Shannon was very quiet. He wasn't bombastic or self-aggrandizing, and that speaks to his character. So Shannon was born in 1916, in the middle of World War I. And he was a tinkerer. He was fascinated with things, the magic, the eloquence of the way things worked and why they worked the way they did. And he spent his youth building things. For example, early on he built a telegraph system based on barbed wire as the conductor. I mean, he played around a lot. Now, I want to make that point as we go along because I want to get into his character before I talk about the anecdotes. He was not the classic researcher who goes out there and writes and publishes papers, although he published a lot of papers. Okay, that's the collection of all of his work, and they're all great papers. But that's not what motivated him. He was interested in, seeing why magical things work and how they work and why they work that way. The how is engineering. You look at a device, you build it, you break it, you tear it apart, you experiment with it, you test it. How does it work? You learn, and as a result of that, you get enormous intuition and understanding as to how things behave. But the other half of the argument is why it works that way. Why does electromagnetism work? Why does certain aspects of machinery work? It's the physics and the mathematics that helps you explain the why, whereas you've learned about the how. Now, most scientists are good at one or the other. It's rare you find people with both those talents, and that's a winning combination. And I encourage you to try to think in both those domains. It really is important because it'll allow you to see things you wouldn't see otherwise. So early on, he worked with some of the greats that you know. He worked with Turing, he worked with von Neumann, he worked with Wiener, and I want to tell you a little story about Norbert Wiener and Shannon. They were both working on research during World War II, and they were both trying to basically develop technology which would help. Wiener was concerned with shooting airplanes out of the sky, automatic fire control. The way it worked is you send a radar pulse up, you get a reflection, but it comes back with noise. You get a noisy measure as to where that aircraft is or where it may be going. So you have to get rid of the noise. You have to do prediction and extrapolation and smoothing and decide to shoot where the plane's going to be. It's a very sophisticated theory. And Norbert Wiener, if you've never heard of him, he created something called cybernetics, a word which people don't really understand. But it was about control theory. Brilliant guy. That's a whole other discussion. The stories about Wiener are wonderful. He's absent-minded. He graduated with a PhD, I think at about 18 out of Harvard. He was a misfit. He was absent-minded, thick glasses, and an amazing guy. But, so he was interested in this. Shannon was interested in sending messages over noisy channels. Same kind of thing. What you receive is a signal plus noise. What do you do with it? I'm mentioning that because they both came upon the same beautiful idea independently and around the same time. It was the following. We all knew that the way to characterize noise was statistically. It's unpredictable. Use probability theory, stochastic processes. But both of them said, you know, the signal is also best described statistically. Because if there's no uncertainty about what the signal is going to be, why send it? So he added statistics, both of them, into representing signals, and that broke through brilliant fields. Wiener developed basically signal processing. Shannon developed communications, etc. Because Shannon added one extra piece that Wiener didn't. Wiener said, you measure, you receive the signal, process the hell out of it. Shannon said, look, before I send the signal, I'm going to prepare it so it's best resilient to the kind of noise I expect it's going to meet. So he did encoding and decoding. Whereas Wiener just basically did smoothing and extrapolation after you receive it. So that's an example of the kind of brilliance that both of them, in this case I'm talking about Shannon, there was something unusual about the system. When he, his master's thesis, 1937, basically, was to show that Boolean algebra was the right mathematics to describe switching circuits, computers. So he introduced the idea of Boolean algebra, which we all use now, for describing switching circuits and chip technology, etc. Brilliant piece of work. Master's thesis. Then he went on to get a PhD, and I believe the story is correct that he couldn't get into the PhD program at MIT. The idiots wouldn't let him in. So he went off and did a wonderful piece of work on the algebra of genetics. He put together a mathematical structure of genetics. It was a very interesting piece. It never really went very far. But he then went to Bell Labs and did this brilliant work on the mathematical theory of communication. You're going to hear about that. But the point is, at that time, communication theory was a kind of mess. They had FM, they had AM, they had different modulation schemes, different noise models, but there was no understanding of the whole picture. And that was a perfect challenge for Shannon, whose mind was, well, I sort of see how things work, but why do they work that way? And what's the global comment about it? And he put together this wonderful theory of information theory and coding theory, which explained it all. It was a brilliant move, and it still has, it's resonating, of course, last century, this century, it'll go on forever. Brilliant ability to bring the field together. So, got a few stories I want to tell you now. Let me pull them up. He got his PhD. Edison, by the way, was a distant cousin of his, just by accident. An example of the kind of thing he did was the following. He wanted to predict how much uncertainty is there in printed English. Now, you guys don't have a book. I'm going to pull this one up. This is not a random book. It's about mathematics. Anybody have a newspaper here or a magazine? All right. I'm going to go to a random page here, and I'm going to start reading to you. And when I stop, I want you to predict what the rest of it says. So I'm going to give you some context. He wanted to calculate how much uncertainty is there in printed English. Now, if you assume there's 26 characters, rounded up to 32, how many bits do you need to represent that? 5 bits. But not all the letters are equally likely. So how many bits do you really need per letter in printed English? Well, you can start with assume they're all equally likely, or then put in the real word frequencies, or the pairs, or the triplets, and then the word, etc. And the context. So I'm going to help you with the context. I don't want to make it too technical. Here we go. Evidently, the proper correction to apply to the amount of information transmitted is the amount of this information. Now I'm going to stop. And I want you guys and gals to predict the next letter. And either you'll get it right or not. So I'll read that again. Evidently, the proper correction to apply to the amount of information transmitted is the amount of this information. What's the next letter? Well, actually, space is next, but I'll give you that. Space is an allowed answer. What's the next word? Letter? T. You're all wrong. So you get an X, okay. It's W. What's the next letter? Ah, good. H. Correct. Next. Well, let's decide. I-A-E. All the vowel. Well, I'll give it to you. It is the I. Okay? Yes? Next letter? Space. Right. Good. Let me see what the next word is here. Okay, next. He's correct on I. You said C. I'll give you half, okay? Good. Good. Okay, now we can go on. It doesn't matter what it says here. It turns out if you do this experiment properly, people can predict 70% of the characters, which means there's enormous redundancy in English. And Shannon actually went to predict and calculate bounds on how much uncertainty there was in each letter, and it's certainly not the 5 bits. It's like 1.4 bits, more or less. There's upper and lower bounds. Yes?
So, what did you know this 70% figure? Maybe like people were given the next letter if they got it wrong.
No, it was experimental, the way I just did it. And typically, groups can get about 70%, more or less. Depends upon the text, depends upon is this newspaper, is it a technical book, etc.
I was asking, like, was it like pretty much this exact same method where like, if they got it wrong, they would get the answer?
Yes, if they got it wrong. And it wasn't a group, it was an individual, so they could say yes or no. Yes?
Did your accuracy go down, like, the further you got from the sentence or the sentence?
No, because you're seeing the text.
Oh.
At every point, you know everything in the past. But the more I give you up front, the better you do. But it tails off fairly quickly. Context goes back just so far, and then it gets a little noisy. Okay. Now, when Shannon did his mathematical theory of communication, I'm going to give you a quote that he said. He said, "My greatest concern was what to call it. I thought of calling it information, but the word was overly used, so I decided to call it uncertainty. When I discussed it with John von Neumann, he had a better idea. Von Neumann told me, quote, 'You should call it entropy for 2 reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name, so it already has a name.' Some of you who studied statistical mechanics know entropy is an important concept. In the second place, and more important, no one really knows what entropy really is. So in a debate, you'll always have the advantage." I mean, so I'm building up sort of the playful side of Shannon. He loved fun. He loved surprises. He loved to fool you. And when he went to Bell Labs, besides his great work with wonderful colleagues, he would ride a unicycle down the halls of Bell Labs while juggling, while going down the stairs. I mean, he was a strange phenomenon. If any of you know Marvin Minsky, one of the fathers of artificial intelligence, Shannon had one time Minsky in his basement and asked Minsky to stand on a plank which was resting on top of a billiard ball. Not a billiard ball, a bowling ball. Well, Minsky broke his elbow. But Shannon could do that. I mean, he was a juggler. He loved to build things. He built mazes you'll hear about in here. So let me go on. So after I got my master's thesis at MIT, I was done. I scheduled my son to be born right when I finished. I'd been working at MIT. They gave me a wonderful research job, good pay, working on my own in the research lab. But my thesis advisor, my master's thesis advisor said, you got to get a PhD. And I said, I don't want a PhD. I'm very happy where I am. He said, you got to get it. So I continued to twist my arm. I finally, okay, I'll do it. I said I had two conditions. Condition number one, I want to work for the best professor I know at MIT. These are my internal conditions. And second, I wanted something important. So who is the best professor I knew? Claude Shannon. I'd taken his courses. I had met him. So I called him up. And I said, I'd love to do my PhD research for you. And this was in the middle of the week. He said, fine, come on over to my house on Saturday. Well, magnificent. I mean, how could you turn that down? So I went to his house, but he told me, I hope you don't mind, I have a guest in the house, John Pierce. And I said, I don't mind, I'm coming to see you, he's a great man. So I told my colleagues at MIT where I was going, and they said, oh, John Pierce? Now, John Pierce, in that day, was a wonderful opera singer. So my friend said, when you get there, ask him to sing the Bluebird of Happiness or something. So I got there expecting to meet John Pierce, who was a rotund person. I get there, this skinny guy answers the door. He says, I'm John Pierce. Totally different guy. John Pierce, totally different guy. He was at Bell Labs. He worked with Shannon, and he was visiting Shannon. But he was a real pessimistic guy. And I come in there bubbling. My son had just been born a month before, bubbling over with, new father. Boy, what could be better? Child, it's all the rest. And Pierce says, bah, humbug. He says, children will only disappoint you. And I mean, I couldn't believe it. But so I got to meet Shannon, and we were sitting on his porch, and he was sitting in a chair here, and he had me sitting here, and we're talking about possible research topics. And then I noticed his eyes looking above my head, sort of going back and forth. So I turned around, and his son was in a hammock, and the hammock was coming within inches of my skull. Had I turned around carelessly, I would have been knocked out. But that was Shannon. But he agreed, yeah, I could work with him. What was he going to do? He was very much interested in chess. He loved games. He loved challenges. And he had already written a paper which talked about a program for playing chess. By the way, he didn't implement it. And a guy named Arthur Samuels read that paper. Arthur Samuels was working at the Iliac 1 system at the University of Illinois. And he decided, well, if he could do chess, I can do checkers. He was going to teach a computer to play checkers. Well, it turned out that Shannon had not built the damn thing, only talked about it. So Samuels had to face the problem of implementing a checker play program. And he did it quite well. He finally worked at IBM. And when they launched the IBM 701, they announced that it could play checkers. And the stock of IBM went up 15 points overnight as soon as it happened. It was a great checker playing program. Side story, am I taking too much time here? The side story is Samuels was one of the first to have the machine play against itself, and any game program was really interesting. And it was using alpha beta pruning and search. And he also would play with it, or against it, if you will. So one day he was playing with the machine, and he accidentally changed the algebraic sign of the objective function from plus to minus. The machine was now supposed to lose, and Samuels didn't know that. So he started playing with the machine, and he couldn't tell the machine was trying to lose. Because to lose good, you got to capture control of the board and to make the sacrifice at the very end. Well, that should scare everyone in this room. If you give the United States economy to an artificially intelligent program and say do X, Y, and Z, and if it doesn't do it, and if you can't tell how it's doing until it collapses, that's dangerous. So unless we get to explainable AI, there are some issues, but that's a whole other discussion. So he wanted me to work on chess. Now, he wanted to get a system that played the middle game in chess where all the interesting strategy takes place. And John McCarthy, the other father of artificial intelligence, was there at MIT. And he was going to work with Shannon. And McCarthy had a student named Paul Abrams. And they were going to develop a program to generate legal moves from any position. What are all the legal moves? Feed that to us, and we'll figure out which one to take. So what should be the strategy? Well, there was a book by a fellow named Fred Reinfeld called 1001 Billion Chess Sacrifices and Combinations. Had 1,000 pages, and each page was a position. And it would say, white has a brilliant sequence, go find it. Or black has a brilliant sequence, go find it. And these were all hard. You know, I was an okay chess player, but it was almost impossible to solve those things. But in the back were the answers. And Shannon said, look, go to the back, look at the answers, and find out which is the most common move for the first move of a brilliant sequence. What's the first move people typically take to get into a brilliant sequence? And what's the second most common move? What's the most common second move, etc.? Well, guess what is the first most common move of a brilliant sequence? No. Check! When you check the son of a gun, there's not much they can do. You can see the sequence down. Well, obviously, right? We didn't see that until we looked at the answers, you know. And then the second most common is a capture, or a fork, or whatever. So we programmed that thing. It eventually became the MIT chess playing program, but I said that's not what I want to do, so I went off to do other things. And Shannon was on my committee. Let's see what else. He also supervised a classmate of mine sitting next to me in the research lab, a guy named Henry Ernst, who was building basically a mechanical hand with a photocell, so it could look and it could move around. It was an ugly looking thing, but it could move around and do some interesting things. And it was a nice piece of work. He graduated, his desk was empty. One day his phone rang, so I picked it up and they said, this is the Boston Globe. We want to interview Henry Ernst. I said, no, he's gone. He's already left. I said, oh, we wanted to talk to him about his mechanical man. I said, it's not a mechanical man, it's a mechanical hand. They say, what's the difference? So there you see the way the press takes an idea and expands it, and basically what comes out is fiction as opposed to truth. Okay. Let's see. Okay. Now again, Shannon came to MIT in 1956. I got there in 57. And he was not doing much supervision of information theory, but he was supervising artificial intelligence, things, etc. And one day he and another faculty got up, spoke to the graduate students, and talked about a project they wanted to do to build a mechanical hand and robots, etc. And just to give you an idea of the way his mind worked, he pointed out, if you ask a robot to move its arm, it'll move like this. But that's not what a human does. A human does this. It's built to feed you. Noticing that little difference already gives you insight as to how you want to build these devices. Just he always looked at what's interesting, what's puzzling. He wasn't interested in the applications. He wanted to solve interesting problems and understand why they work and how they work. He built a juggling machine. Damn thing would juggle, but it didn't juggle up, it juggled down. Because he can predict much better where the ball's going to bounce than throwing, you know, sticks up in the air. He was not very, what shall I say, wouldn't give praise very often. He wasn't a mean guy, but he wouldn't just say, oh, that's really good, when it was, yeah, so-so. So I remember one day I walked into his office and I showed him what I was doing. And the biggest compliment he could give was he said, now you're cooking with gas. And if anybody understands what it means, you know, you're really using the right stuff. But I remember one day I walked into his office and I had just solved a problem. It was a complicated problem, had a very simple answer. And I asked myself, why is it that simple? You know, I didn't see the intuition. So I went to Shannon and he got it in 5 minutes. He saw exactly what about that system made the answer so simple. He just had that ability. But you walk into his office another time, this brilliant mathematician, this great man, what is he doing? He's sitting at his desk with a differential gear in one hand and a Swiss Army knife in the other, and he's unscrewing the goddamn thing. I mean, that was Shannon. He was interested in, I'll call them toys or puzzles or devices to play with, to figure out, to fix. So he wasn't interested in the applications. He was interested in, you know, let's play. He was a tinkerer. And those of you who have any of that in you, and I'm sure you all do somewhere, I encourage you to reinforce that. Keep that amazement as way things work, you know, and try to find things to figure out, gee, why is that? As often is said, you know, great results are not usually accompanied by saying, Eureka, I found it. It comes when you say, that's funny. Why does it behave that way? And that's where the gold is. When there's something that doesn't make sense, well, figure it out. Figure it out. So let's see, there's a couple of other things I wanted to go through. Oh, yes. So when Shannon was trying to figure out the entropy of English, he needed to know what the first order statistics was. E is the most common, E-T-A-O-I-N with probabilities, and the pairwise, and the triplets, and there were tables with that information. But then he wanted to get to word frequencies. What's the most common word? It happens to be the word the, by the way. And it turned out that a fellow named Zip, Z-I-P-F, whose name you may have heard of in power law studies, had written a book called On Human Behavior, The Principle of Least Effort. And in that book were tables of the word frequencies. He had collected them. He collected an enormous amount of statistics. Great. And then in there was also data about how much traffic or commerce was between two cities in America, Chicago and New York, Boston and Washington. And I had to build a sample data network, and I wanted to get some real numbers. So I wanted to borrow the book from Shannon. I did. And I used some of the numbers that Zip had, which was actually very nice. And then a few months later, Shannon came to me and said, do you still have that book by Zip? I said, yeah. He said, I'd like to borrow it. I said, well, of course you can borrow it. It's your book. And then I said, but why do you want to borrow it? And he said, well, I'm making a model of how wealth is distributed in the United States. I said, why? He says, well, I'm building a model for the stock market. And, you know, I want to take advantage of it. So you got to picture this. I'm a graduate student, figuratively small relative to this giant of a man who wasn't much bigger than me, but figuratively. And I said, you mean you want to make money? And he looked down at me and he said, yes, don't you? I mean, of course, but, you know, beautiful, beautiful story. Let's see, I think there's one other thing I wanted to talk about. Oh, yes. This is a comment on the way generations of researchers treat those who came before them. So some years after I graduated here at UCLA, I went back to MIT and gave a lecture to a very large group. And I invited Shannon to come. And he came. And I gave the lecture. He liked it very much. And I was chatting with him afterwards. And I said, how often do you come to MIT these days? And he said, I don't at all. I said, why not? You know, the benefits so much. And he said, they don't invite me. The young Turks like to push out, call it competition or the old guard. And it's a great mistake. It was true for Bob Finer also. It's a mistake, and it's a great shame. And some years later, you know, he used to come to LA. We'd go to dinner together. And what would he do when he was here? He'd go down to a store in downtown LA and wanted to buy a chess playing machine. There were machines that could actually, well, they were smart and they could move the pieces. You move your piece, it thinks, it moves its piece. And there was a shaky little arm that comes and gets the bishop and moves it over. And if the pieces aren't exactly where they belong, the machine goes there and it doesn't find the piece, and it goes catatonic, you know, and it starts jumping around. And Shannon pointed that out, but that was Shannon. Anyway, I'm done. Enjoy the movie.